morning or afternoon or evening, and happy lunar new year. Happy, how do you say? I cannot say that. All right, so we start the lesson today. It should be the third practicum, but again, Yann stole the first one, so I guess it's the second practicum. We are a little bit staggered, but we'll figure how to catch up. I started this lesson with sharing a few tools. You don't have to use them. This is what I use. I like them a lot, and I think if I like that, perhaps you may like it, and that's nice, right? Nice sharing tools, I think. So one thing that I've been sharing, I also shared last year, it's this software to take notes, which is called Typora. And this software here allows me to write, okay, I don't know, I'm messing up. How do you change the zoom? Zoom in, zoom out, zoom, with a shift. Okay, there we go. So here I can write Markdown. All of this is Markdown, but then also I can write LaTeX, okay? And so this is like very convenient way to take notes for papers, I think. It's called Typora, Typora. It's free. Works on every platform. I like it. Another tool that I've been using, I started using it recently, but again, it's free for students. It's this thing called Notion. This is my control room. Here I have things for work, like do many things. These are private life, I don't know, gather pictures from Christmas. And then you can also have like pages with inside things, right? Like I have a page with media, and inside there is all type of media I'm consuming from the internet, right? Like these are blog posts, like blog, website, to do, priority, subject, and then like, I don't know, the author and so on, right? Another one, it's like, I don't know, books, for example, that I will start reading. I just started this stuff. This is all personal development. Maybe I get to improve myself, or cooking, right? So I just started again. I have another database with some recipes. I think it's very nice to have like things in one place. And I'm gonna start using this for research as well. I have articles. And here, for example, you can have a database with all possible articles that you've been reading and write notes. Each of them you can open, and then inside you can actually write LaTeX as well. Okay, so it is LaTeX, supports LaTeX. So I think it's super cool. All right, promotion done. I'm not getting paid, right? So it's not promotional message, but I think it's nice. Someone say about Obsidian. I haven't tried. Perhaps it's good. If you didn't know about this, now you know. If you knew already, okay, sorry to waste your time. All right. So before starting the practicum, today we're going to be talking about training. But before talking about training, I need to make a very big distinction and be very clear about the fact that if someone uses gradient descent, question to you. I'm reading the chat, right? How does someone train a network? What is the procedure for training a network? What is the algorithm that one uses for training a network? Answer in the chat. Gradient descent, yes. Okay, that is a correct answer. All right, so gradient descent is actually the correct answer. All right, so every time rely on PyTorch. Every time I ask this question so far, now I don't know why you know the correct answer. Every time I ask this question in class, everyone answers backpropagation. And then I get a little bit, I wouldn't say annoyed, but maybe yes, annoyed. I'm joking, right? What is backpropagation? If I ask you, right? Maybe you watch my videos already, but okay. If I ask you, what is backprop, right? What is backprop used for? Job interview, right? If I ask you, what is backprop used for? A way to compute the gradients. Cool. And that's it, right? So you don't train with backprop. Backprop just gives you the gradient. The training happens by stepping, perhaps using the gradient, right? Which is the gradient descent. Okay, fantastic. You already know everything. All right. So if I'm showing you this chart over here, I'm going to be talking about inference here. Oh, this is another software, right? So I show you another one before. This is a third tool. Okay, so this is called, how do I hide this bar? This one. So this is called draw.io. Now they changed the name because I don't know. All right, so here I use all these shapes to draw the diagrams that Yann pointed out, right? So this is an observation because there is a grayscale, like there is a gray background. So this is an observation. I feed this one inside this item here, which is an encoder, which is a delay in the advanced palette, okay? And so I get my y bar. So my y bar, I put the x inside this function. So how is called this procedure? Do you know? It has a name. I mean, a stupid name, but before we talk about backprop, this is called, if it's not backward, it's type down something in the chat. Forward prop, yes. All right, cool. So this is forward propagation, right? So you get an output y bar, given that you provide an input x to this module here. So this is the mathematical formula, which is like written in the wrong direction, right? I mean, the things I usually read from left to right. So x goes through the encoder to give me a y. And here it's written y is given by f to which you input an x. So again, I think the graphical version is more intuitive. Cool. So how about this thing over here? What do you see here? Can someone describe to me in words on the chat? What's the difference between the second row? Inference with new example, okay. Both of them are inference, okay? So when I compute something given something else, it's called inference. So both of them are inference. But then what's the main difference so far of these two drawings? Can you tell? Can you spot the difference? It's like, you know, I can see the bar over the x, that's the first point. And then the second thing is that the observation is the output, okay? And so there is no bar over the y. Yeah, so there is no bar over the y. This is the observation. It's grayscale background. The bar is on top of this guy, right, over here. And so how do we find this x bar given I have my y? Anyone can guess? Backprop, yeah. I mean, okay, decoding would be using a different module, right? So decoding would be actually having here one of these guys flipped in the other direction. You feed this decoder with this y, and you're gonna get a x. So that's that is something called how is it called? Blah inference. Hold on. Okay, judge, and if you can type down, I forgot. Okay, it's called blah. I forgot the word. No, it's not target. Okay, I'll let you know later on. I forgot. But it's called something amortize. Yes, thank you, Vlad. It's called amortize inference. But you can do the inverse, but we don't do inverse. So what we do actually, okay, it's the following, right? So here you're gonna get the x is going to be the outcome of performing a minimization over how far the network output is from my target, okay? So yeah, Jacin pointed out target prop. So we have a target, which is our actual observed y, which is this y without the bar. And then we have something that the network output, okay? Which is this thing over here. And then you just do gradient descent such that you get the network to shoot to as close as possible to this y by changing x, right? And so finally you end up by using gradient descent with the x that has the model provide the closest answer to our target, okay? It's not tractable. This is like gradient descent. It's neural networks, right? Right, so parameters are fixed. The network is given to you already. like before, no one asked me, about the parameters of this network here. So here we already assume in the first case, right? Who was asking? Colin. In this case, no one asked me, are the parameters fixed? Yes, of course the parameters are fixed. Here's the same, right? So this network is already given to you. How do you find the input that gives you a specific output? By minimizing the difference between what the network actually outputs, which is this one, with the actual observation, right? And so this is still inference, but the outcome, like the output of inference, is a solution of an optimization problem, right? And so again, if someone's asked you, is backpropagation used only for training? This is an important question. Let's say it's an exam question, right? We don't have exams, but okay, whatever. So if you see this question, right, job interview, is backpropagation used only for training? Answer. What do you answer? No. Okay, good. All right, that's it. Nope. Okay, fantastic. All right. Try out this one, draw.io. And use these diagrams, right? Delay and then the circle. You can also turn on the LaTeX extra, dark theme, of course. So do you know why I use dark background? Do you know why I use dark theme? Because bugs are attracted by light. Okay, all right. Now you know, okay. All right, sweet. So we're starting today's lesson, right? 10 minutes delay, now 15 minutes. But okay, I gave you something already, right? So we learned that backprop is not only used for training every year, but this year everyone answers me that backprop is how we train networks, which is not correct. And you figure that also gradient descent can be used for inference, okay? And actually, we see very soon that this is like what is the standard way of, like the more generic way of doing inference. Cool. So what do we talk about today? Training, right? Yes. So today we are going to be talking about training after I talk about this stuff that is not training. And so we start from here. All right. So again, sponsorship, no sponsorship. Just come over to Twitter and say hi. And that's me, Alf. Okay. Now this is just for making people smile during conferences, like during talks, so people don't get scared. All right. So we're going to be talking about classification. Why am I talking about classification? Because I can show you that everything that is done in machine learning, we can do it in deep learning. And it's a very easy way to explain things, because in theory, you should already know all this stuff. So perhaps I don't have to go that slow. Although if I'm too fast, slow me down. There is a button on the reaction, go slower or go faster, up to you, okay? All right, sweet. Okay, so what is the outcome? The outcome here, well, what are we trying to do? So here I'm just showing you a few spirals, like a few branches of a spiral. And which is simply, I can draw by using a parametric formula I written down there. And then t goes from 0 to 1, right? So 0, you're in the center, then you go to 1, it's going to be the tail. And then you have capital K spirals, right? In this case, we have 3 of them. Let's make things a little bit more interesting, so we can add some noise there. And so you end up with this kind of more realistic, data. So what is the objective of classification? So what does classification do? So I'm asking questions here, right, to figure out what is your knowledge, right? So given this data set, okay, I didn't specify things, right? I'm trying to understand your understanding. Given this drawing, okay, what is the possible way of doing classification here, right? So what is the input? What is the output? What am I trying to do? Type in the chat. No one writes anything. So this is not okay. Multi-class classification. Yeah. What am I trying to do here? What is my objective? Define decision boundaries. Oh, okay, too many people, right? Okay, so define decision boundaries. Okay, perhaps. Input should be a data point. What is a data point? Okay, what is the size of the input here? Okay, input are points in a 2D space, right? So a 2D coordinate is one of these points here, tac. This is the 2D location, right? The X and Y location is going to be my input. What is my target? So what should I, given this location here, what should I do? The color, right? I should say red. If I take this dot over here, what should I do? I should say it's yellow. If I take this dot over here, I should have my classifier say it's purple. Okay, sweet. So what is the easiest way to do classification? Just linear classification, right? I mean, I'm just drawing straight lines, right? I'm gonna be doing like this, duck. And so this is my classifier, okay? We're gonna be training this on in a second. Awesome, right? What is the problem now? Error, okay, what is the error? What is the issue here? So, okay, sweet, that was the keyword, right? So these regions here, like these branches, these spirals are not linearly classifiable, separable, right? So I can't use possibly a linear separation, a linear boundary here to tell apart different spirals, okay? And so how do we deal with this, right? Well, so again, the issue here is that there are all these intersections that are gonna be, not leading us to have a good result, right? All right, so on the left-hand side, this is what, when I was doing my PhD, I was naively thinking, oh, my network is unwarping the space, right? Like that. Basically here I undid my, my parametric function. When I train a network instead to fit this data, from the input perspective, where I still see all these things in the input space, I can look at the final decision boundary, which were linear, because we only have, each module is linear, but then we have a non-linearity, right? So if I look at the last one, it's going to still be a linear. But then if I look at the output from the input, I can see how these output linear boundaries will be morphed around, okay? So this is, on the right-hand side, is what usually you see in most of the tutorial online, on blog posts and so on. But I don't like it. I like more the left one, right? To see how things are warped around, right? And that's why I show you last time in the first lab, this animation, right? Which is gonna be coming up as soon as I show my screen again. All right, here. All right, so at the beginning, I show you these 5 branches. Again, each point is a 2D location, and then I have capital K equal 5. So I have 5 different possibilities. And this is actually what really happens, right? And so what I'm doing here, I'm just doing a linear interpolation between my input to a embedding layer. I'm going to be drawing this in a second. But what I'm trying to show you is that before getting to the output of the network, this embedding layer, which is going to be shown to you in a second when the animation ends up, like finished, complete, you see that these classes are now linearly separable, okay? So all the previous chunks of the network does is going to be basically warping this, this space, right? I like to call it space fabric because it looks like, a piece of napkin. And so the point is that the network unwarps what is this data, no? And lets you have it linearly separable. And then I use different planes. So this green one over here, it's a plane that goes up this direction. Then if you have another plane going up the other direction, it's going to be a yellow one. The intersection of the 2 planes is going to be a line, right? So you have this line over here. Then if I have a third plane going the other direction, you have an intersection between a plane and with a line, which is going to be a point, which is this point over here. Instead, this one here is going to be the intersection between the yellow and the blue. But then I have another plane, no? And so you have another line here, and so on, right? So here you have basically 5 planes. And if you don't know why there are 5 planes, you can spend more time with the math and playing around, but that's not important. Here you can see how the final layer can be separated by these intersections here, you can see, these are intersections between planes, okay? So there are basically, I can call it even hyperplanes, right? So there are basically, I can chop this space that was unwarped. Before it was all warped, it was impossible to linearly separate. Now the neural net basically unwarps the space such that it can be linearly separable. Cool. So what am I showing over here? And now it's going to be drawing time. So what I'm showing you right now is going to be is the following. So here I show you a network which has 2 inputs, which are my x and y coordinate. Then it goes up to 100 neurons. These are 100. Neurons. So my first matrix, what's the size of the first matrix? So if I have here my W1 matrix, this is a matrix of size whose 2 times 100. Are we sure? Okay, we are always using column vectors. Okay, thank you, 100 by 2. So the height of the matrix is going to be the dimension I'm shooting towards. So this is going to be 100. And then the width of the matrix is going to be the dimension I'm shooting from, okay? So I look from here, and this is going to be where I'm going to. So I have 100. So the height is what tells you the outcome. I mean, if I use column vectors, right? I know I draw them horizontally, but because I tell you why in a second why. So then here I have my nonlinearity, which is going to be a ReLU. And then here I'm going to have down to 2 neurons again. And then I have 2, 5. Okay? And the network, this is the input, right? Input, this is the output. And networks are always going this direction. Why is that? Because you go high in the network, you go high in the hierarchy. So what you have here on top, it's a classifier, right? So usually people say, oh, you just put a classifier on top, right? So this is my classifier. This is a linear classifier on top, right? Cool. So why do I have this intermediate layer over here? Well, in this way, I can do a linear interpolation between this guy and this one, right? So I can do like 100% this one, then I have 99% 1%, 98 2%, 97 3, and so on, right? And so that's how I show you the animation before. And how did we train this network? Well, we're going to be covering this right now, okay? The important part here is that I use here 100 neurons in the intermediate representation, okay? And this is why things are so nicely behaved and smooth and work so nicely. Later on, before the end of the class, I'll show you a network which only uses 2 neurons. And it actually is a very deep network, but only has 2 neurons all along, okay? So possibly a network with 2 neurons can move things in a plane, right? But the nice part here with using 100 neurons is that you can move things in 100 dimensions. So you have much more freedom of moving things around, and then you can project them back to 2 dimensions. And going in high dimensions, things are much more separated and more easy to move things. So the what's called the optimization process in a high dimensional space is much easier, right? Things are not constrained. If you try to do a optimization process only by using 2 items, like I show you right now, like a network, very tall network, but having only 2 neurons each layer, try to train the thing is like a nightmare. I tried, I managed to make it work, but again, it's like more of a hack, and I show you as well the outcome, okay? So this is just to give you a small like explanation of what I show you on the first lab, okay? Clear so far, right? Let me see, yeah. So far, everything is fine, right? So this is half class so far. Yes, no. You have thumb ups, thumb down, green circle. 2 green circle, 3, okay. Okay, all right, 9, 8. Okay, there is a portion of the class who's following. There is someone clapping, okay, yay. All right, sweet. Let me move this bar away again. So we're gonna go back to the slides and let's figure out how we train these networks, okay? And every time I present something, this bar appears in front of my face. There we go. Okay, bar away. Okay. So training data. So the network we saw last time, on the second practicum, that they perform arbitrary transformation of these points. Then we have to enforce the basic transformation to be like, following a specific, like to be instrumental to our task, right? So now we would like to do classification of points. So I have to introduce the training points. So my input, which is going to be always in pink, and it's a bold vector. So it's a bold symbol, which means it's a vector. In this case, for me, my x, the example I, is going to be belonging to Rn. So there are n components in x. And then here I have my capital X, which is going to be, it's called my design matrix, where it has all my column vectors lying on the side, okay? So in this case, my X with the parentheses are the horizontal, the transpose version, okay? And so I have all of them stacked on one after each other. And this is what happens as well in PyTorch, okay? But again, this is the design matrix. So I have n columns, and then I have m rows. On the right hand side, instead, I have my CI, which is going to be my class, right? It can be 1, 2, for example, 5 in the last animation I show you. So here I have my collection, m items, right? 1 per each sample. So the x1 will have the c1. The x2 will have the c2, right? The class number 2. The xm, like the input, so x means input for me, right? So the m input will be associated to the class cm. So I have m labels, right? So these are my labels, my classes in this case. So I have 3 or 5 classes, but these are the labels associated to each data point, okay? A way to encode these labels is going to be using the one hot. So what's one hot? One hot simply says, since 1, 2, 3, there is a like ordering, like in the numbers. I don't want to use ordering. I just use a vector of all zeros and only one, only a 1 in the position, which is, representing my given class, right? So if I had just 3 classes, I will have these vectors here that will have 3 components, right? So ideally, this thing will have capital K components, right? And so this one refers my first is my first item, right? Like first class, second class, third class. M is the number of data points, right? So I have 1 to m data points, and therefore each data point will have its label. So C1 is the label for the example X1. C2 is the label, for the X2, right? So XM belongs to class CM, right? So CM will be, 1, 2, or whatever. C is the output label. C is the label. No, C is not Y. I didn't talk about Y. Why? Who's talking about Y? K classes distributed as labels over M points. That's why, yeah. So far, everything's okay, right? I think so. Otherwise, please, Vlad, judge and answer questions I cannot catch. All right, cool. So what do we need now? So now I'm going to be introducing my Y. So what is this Y? Y is going to simply be, in this case, my one-hot encoding of these numbers, okay? So in this case, there will be capital K columns, right? And then I'm going to have M rows, right? So one Y per given X, and the given Y will have a 1 in correspondence to the index represented here, right? So if this is 2, then you're going to have this guy here, right? The second item is going to be set to 1. If CM is 3, then you will have this, Y is going to be equal to this one, okay? Capital C is the class index. There is no capital C. There is lowercase c. But yeah. Y is one hot. Yeah, okay, Justin is explaining. Sweet. All right, cool. So here we have that my yi, right, the ith sample, the ith label, basically. It's a 0 or 1, right? It's binary with capital K elements, right? So you're going to have as many elements as capital K, and then the kth, or the kth element is going to be set to 1, right? Which is told to you by this number. Meaning, if this one is going to be red, you're going to have the 1 on the red. So this is going to be red, purple, yellow, right? So if this coordinate here should be yellow, you're going to have the 1 in correspondence to the yellow column. If this point here is supposed to be purple, you're going to have the 1 in correspondence of the purple. So each column is going to be red, yellow, purple, okay? And each of these rows is going to be 1 2D coordinate. I show you in the drawing before. Cool. So fully connected layer. Again, we are revising this one. So let me know if I'm going too fast. I have my input at the bottom. Then I have a matrix, WH. It's bold, so it's a matrix. You know this already now. Then we go to a H in green, which is my hidden layer. Also, this one is bold, which means it's a vector. And then we're going to have another matrix, WY, which is going to be mapping. It's going to be rotating H to go to the final Y hat. So these are the equations, basically, like the only equations we're going to be seeing, basically. We have the H is going to be my squashing function F applied to the affine transformation of the X, right? And then you have that Y hat is going to be this squashing function G applied to the affine transformation of this part here. And we already watched and seen this very extensively last time, okay? In the previous practicum. And this squashing function can be the positive part, the sigmoid, the hyperbolic tangent, the soft argmax, and whatever you want, okay? So let me draw this in an extensive manner, right? So this is like a more condensed neural diagram, right? Where these are supposed to be like clusters of neurons. Here I'm going to be drawing each separate neuron. So this is my input neurons, also called X. Then I have my, let's say, first hidden layer. That's why it's called H for hidden. Then I have the second hidden layer. Then I'm going to have the third hidden layer, and so on until I have my final output layer. And so here I can see there are the first layer is going to be called also A1, like the activations of layer 1. Then you have layer 2, 3, 4, until the last one. Now we have five layers in this case, right? So for me, layers, and it's basically, well, the layers are the collection of neurons. And I do count the first layer to be the input layer. And to move from the A1 to A2, you're going to be using the matrix W1. Then you have matrix W2, W3, and W whatever L, okay? So how do we compute, let's say, the first hidden neuron, right? So let's focus on the first element on the hidden layer, right? The first hidden layer. So this item here will be simply be my AJ, right? The jth neuron at the second layer, which is going to be my squashing function applied to this scalar product between the WJ and X plus this bias term over here, right? So first of all, what is WJ? Well, WJ is simply the jth row, right, of the W1 matrix. Again, you should write down on a piece of paper if this is not like clear. And what is the scalar product? Well, simply is the summation of all the product, right? So the element-wise, like you have like the element-wise product, then you sum them all, and then there's going to be one more offset term here, and then we apply this squashing function f. And so basically you have that all these input x on the left-hand side are multiplied by some coefficients that are those w's. They are all summed together and displaced by the bj term to give you the first value, which has to go through this squashing function. Second one, same stuff. You have all the inputs multiplied by a second bunch of weights, which are these weights, the coefficients. They are summed together, then we displace by the bias term, and then we apply a squashing function. Is f function a kind of sigmoid? No, f can be anything. It's written down here, right? F can be the positive part, like ReLU, the sigmoid, hyperbolic tangent, the soft argmax, whatever you want. It's just a non-linear function, because if you only have linear function, what is a linear function of a linear function of a linear function of a linear function? Linear function. Okay. Actually, I mean, yes, on paper, not on computer. So there is a paper from last year where they train a network which doesn't have nonlinearity, still works. They use the floating point approximation as nonlinear function, but okay, you know, whatever. All right. So that's why we need to put something that is nonlinear, right? Piecewise linear. What that was the question? No, if you have a linear function of a linear function of a linear function, it's still linear. There's no piecewise. Piecewise is if you use a ReLU, which is basically selecting regions. All right, so how do we get the whole layer? Well, you just do the same for all of them, right? Boom. And this one is done in PowerPoint. So I drew every line by hand. Don't do it again. Like, don't try to replicate, okay? Thank you. Okay, painful, okay? Then guess what? I have all these weights collected in that matrix down there, okay? Same for the second hidden layer. You try to do copy and paste, doesn't work. So I had to draw again by hand. Because they are not aligned, right? See there is an offset. So again, painful. Anyway, so every neuron is multiplied by, so every neuron here has one weight, then this one has this weight, this one has this weight, this one has this weight. All of them are multiplied by a weight, a coefficient, then they are all summed together here. And then you apply a squashing function, right? Here. And then you get this value and so on, repeat. And then all these weights are stored in this matrix. Now, yes, we can use copy and paste to make the following. And then finally, you end up with the last one, which you're going to store here the weights, and then the final outcome, again, is still thing, right? So, I mean, it's just multiplying values by coefficient, summing, and then applying some nonlinearities, and then storing this stuff in a weight matrix for later usage. What are you using to make this visualization? A mouse and PowerPoint. All right, so back here. Summary, right? So X maps to H mapped to Y. So these are the mapping function, fine transformation to which you apply a squashing function. These are the dimensions. Again, if you just check later, right? If you are comfortable with the sizing, whatever. And then these are the squashing function we may use. So what I want to say here is that my y hat in this case, is going to be a function of my input, right? And so you can think about the network y as mapping, is a function mapping my input Rn towards Rk, right? So mapping this axis towards this y hat. But again, what we really are doing here is actually mapping this input Rn to a usually larger space, intermediate space Rd, and then back to this Rk, right? So usually we have this D needs to be way larger than the input if you hope to be able to disentangle the input, right? So usually the input is really like crammed in a little tiny space, and it's really, really hard to tell apart, right? So that's usually what deep learning has been very successful to do, right? It's been able to unwarp like this thing. So first thing, you need to explode it in a large dimensional space. And then when it's in a large dimensional space, you can move things around much easily. And then when you're done, down back to the domain dimensions, okay? But there is always this kind of upsampling or up spacing, whatever you want to call it. Even if you're using images of 1 megapixel, you still have to go and explode the dimension in a very controlled manner, right? Because if you have a megapixel, you cannot use like a few more millions hidden layers, right? So we covered that in a future lesson, but we still need to go in a higher dimension in order to be able to move things. So this is the answer to the first question from last lesson, right? Why do we go in high dimensional space? Because in high dimensional space, things are easy to move. And so the optimization algorithms actually can work and can move things around. And then when you're done moving, then you go back to the dimensionality you actually work with. Okay, cool. So 2 more slides, then we go to the notebook so that we finish on time, perhaps. So in this case, my input are 2-dimensional. We go to 100-dimensional intermediate representation, then back to 3. Okay, and that was the example I show you. I think I guess for this example here on the spiral, right? Then I use 5 on the animation just to make more prettier in the outcome, right? All right. So neural network training. First slide of 2. How do we train this network? You have a reminder of the equations on the top right. So we're going to be using this soft argmax, okay, which is simply the ratio between the exponential of a given component by the sum of all these other exponential of all the components, right? So you have one component, you take the exponential, you divide by the exp of all the other components. Of course, this stuff will never be lower than 0 or even equal 0, right? You cannot get, like, exponential is a positive function, so you can't go to 0, nor you can exceed or be equal to 1, no? Because the bottom will always be larger, like the denominator will be always larger than the numerator, so it will never reach 1. And all of these quantities are positive, right? So this is within 0, 1 extrema excluded, right? And so the L there stays for logits. The logits is the final output of the network. Usually it's the output, the linear output of a network, okay? That's the definition. So I'm going to define here my loss, my curly L, right? My loss over the entire data set, right? My entire y hat. And so, sorry, my y hat, which is the output of the network, given the whole inputs, right? The whole x. And then the correct class, C. C is the correct class. And so this is going to be simply my average, 1 over m summation that goes from 1 to m of this lowercase curly L, right? And so these are called my per sample loss function. So here I have one outcome, right? My y hat, the ith for the ith input, right? And then the correct class for the ith item, right? And so what do I use here? Well, right now I'm going to be using the following. So my loss, my per sample loss is going to be defined in this case to be the minus log of the y hat at the location told me by the correct class, okay? And again, this is going to be also called cross entropy, negative likelihood. We don't care right now. I'll just show you what I'm doing, right? May I ask why there is a dot on top of the equal sign? That means it's a define, right? So I define it right now. Like, yeah. So what happens if I have an X and my correct class C can be from 0 to capital K minus 1, yeah. No, 1 to capital K, actually. I count from 1 in math. How about X? How about I have an input X and C equal 1, okay? So let's say my Y, no, the one hot version is going to be the first item is equal 1, right? So I count by 1, 1, 2, 3. These are 3 items, right? So C1 means I have the 1 in the position 1 here. And then my network basically says, oh, okay, so given the X, I say roughly 1, roughly 0, roughly 0. Okay, first of all, what is roughly 1 here? Who can say more precisely what is roughly 1 on the chat? No one? Tends to 1, see from which side? It can, yeah, so this is 1 minus, right? And so those other here, what are these? 0, yeah, 0 plus, right? These 2. All right, so if you apply this one to the loss, given the label is 1, you're gonna get the minus log of 1 minus, which is, how much is it? Log of 1 minus is, yeah, there is a minus, right? 0 minus. Then there is the minus in front. 0 plus, yeah. So this one goes to 0 plus. Similarly, if I have the network telling me, oh, no, this is the other one, right? So you're going to be having that the loss is going to be the log of 0 plus, which is minus infinity. Then we have the minus in front, we're going to get plus infinity, right? And so if the network makes a mistake, a very big mistake, you're going to get the loss that goes to plus infinity. Otherwise, the loss is going to be going to 0. I'm going to be showing very quickly this part here, but you are already familiar. So because again, we are going to be going to the notebook. So I have my capital theta is going to be the collection of all the parameters. So all my W's and biases are all here. W stands for weight, B stands for bias, and capital theta is for the collection of parameters. I defined here, I just changed the variable, right? So instead of having this curly L, which is function of the output of the network, I have a capital J function of the theta, but they are the same function. And this is a positive function. So let's assume it looks like this. This is my J, given a scalar parameter only, right? So I have my initial value, my theta 0. I compute the value over here. I have my J at theta 0. I see what is the derivative. The derivative is positive, means I have to go, so this is my positive derivative at the location theta equals 0. And this is a number, right? So all this green thing with the purple, the orange thing, this is just one number, a positive number. And so given that I have a positive number, I know I need to go to the left-hand side. And so I will change theta 0 by a negative. So I have to put on this one minus, right? These positive numbers to go to the left-hand side. And so, yeah, this is my stepping size, right? My coefficient, right? I had to step towards the negative direction of this thing here, no? Because I want to go to the left, given that this value is positive. So I need to put a minus in front. And this is my gradient descent, right? So how to compute these partial derivatives? Well, I just use my chain rule here. And the same for the other parameter, right? So this was with respect to the WY. This is with respect to WH. And so here I'm going to have, the just chain rule. Again, you're going to be chain rule, right? Back propagation. But you already answered correctly to this question at the beginning of the class. So I'm positive you understood so far. In the last 5 minutes, we're going to be looking at PyTorch, okay? If there are questions, we'll take them offline on the campus wire or after we are done with the PyTorch part. Okay, so boom. Again, these go away from my face. Go here. All right. So we go to CD, work, GitHub, PyTorch deep learning. Then you do Conda, activate, PDL, right? PyTorch deep learning. Then we do, I show you that I have this one, right? So this is my Jupyter notebook. Okay. And it's opening here. One moment. There we go. So I'm going to be opening this spiral classification. Let's go full screen. And let me hide the bar. I don't know what happens here. I will choose PyTorch deep learning kernel. And so we're going through the code. I still see you here. Okay, awesome. Let me zoom a little bit. Maybe it's fine now. All right, so I import random crap. I import some drawing libraries. You need to clone the whole thing, right? So there are instructions on the repository. Here I set some default settings for plotting. And then here I choose a device. We already covered device in the other lab. Here I just draw my spirals, okay? So there is no much thing we should spend time there, right? So this is my spiral, okay? And so in this first lab, we're gonna be learning how to train, no? We just apply the things I just show you in the slides. So we start first by training something that is made of two linear models, right? So in this case here, I had that my model is going to be two linear layers. The first one maps from should be N to D, right? So maybe someone should fix this thing because it's bothering me. And now this one goes from my input X that has N dimension to D of the hidden layer. Then we go from D to the capital K, right? So this is my neural net, right? Well, it's a linear model. It's not too nice, but again, that's what we have. So here I define my criterion. And again, if you want to know how this cross entropy works, this is simply the minus log of the output of the correct location I showed you before. You can click inside here. You can do Shift Tab, okay? If you do Shift Tab, you're gonna be opening the documentation. You can place this one in order to see the full description here, right? Okay. All right, so we pick this loss. We pick an optimizer, which is simply doing stochastic gradient descent, which is applying, the negative gradient. And so we're going to be looking at how to train this stuff, right? So how does the training work? So first step, you're going to have that we predict the outcome. So we feed the input to the model, right? So this is going to be feed forward pass. This is step number one. So you have to feed forward the input. Step number two, compute the loss, right? So the loss is going to be simply that minus log blah, 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 which is my criterion over here. And so here is step number two. I provide my prediction and the label to my criterion to get the loss. So step number two. Here I just compute some accuracy. We don't care. Step number three. Step number three is this zero grad. So what does zero grad? So in PyTorch, we never compute the gradients from scratch. We always accumulate to whatever we had before. This is very convenient whenever we use more complicated architectures and whatnot. So instead of just, erasing everything there was before, if there was something before, I just accumulate something on top, right? And so since we just want to compute the gradients in this case, I have to zero out whatever it was stored before. This was step number three. Step number four, we compute backprop, which is computing the partial derivatives of the loss with respect to the parameters, right? So this is my fourth pass, and then the fifth step. So there are 5 steps. The fifth step is going to be stepping. This is going to be jumping in the opposite direction of the gradient. Gradient says, oh, that is the direction of maximum increment of my function. Well, step that direction, okay? So what are the 5 steps? Feed forward, right? You have to feed the network with the input here. Second point is going to be compute the loss, I guess, with this given specific criterion, like cross entropy in this case. Third point is going to be clear up the gradients, because PyTorch keeps like a buffer of all previous, like of the previous gradients. The gradients are the partial derivatives of the loss with respect to the weights, okay? Fourth point is going to be computation of these, basically of the partial derivatives. Backprop actually does the accumulation, right? So if you want to just compute them, you need to clear up this stuff before. And fifth step is going to be stepping in the opposite direction. Is backward just propagation? No, backward is backpropagation plus accumulation, okay? So if you just want backward, you need to clear up. So you need these two things together in order to compute the partial derivatives, all right? If you don't have this line over here, then you will accumulate to whatever there was before. So you just want to get, in this case, new gradients without remembering, regardless of whatever was stored in advance, right? So when we call model X, it actually calls model forward? No. Forward, it does other things. I mean, it does also call model forward, okay? But we didn't talk about forward, right, so far. So this is how you feed a model, right, with the input, given that you define the model in this way. There is no forward yet. Cool. So, all right. So we have the losses. Whatever the, okay, what is the original, what is the first value of the loss here? Now it's 0.86 at the end of training. Question for you, let me know next time. What was the first value? Second question, what is 0.5? How is this model doing? Is it going well? Is it doing bad? Is it random? What is it? Is it bad? Why is it bad? Not great. Is it like chance? Okay, why is it chance? Okay, oh, wait, hold on, 2 classes. How many classes are we training on? Okay, there are 3 classes, so 0.5 is not too bad, right? Yeah, all right, cool. Anyway, it's not either too good. And here I'm just showing you the model, right? So this is the first thing I show you before, right? In the slides, right? So this is my linear model, right? So, okay, not too fancy. I unzoom a little, okay. So this is my linear model, right? A linear model just has linear decision boundaries, right? And that's what I show you at the beginning. But then there are these issues, right? There are like intersections. So one line change, enter deep neural networks, we fix every problem, okay? So let's zoom back in. I can't see anything otherwise. All right, cool. So what I change here, let me just execute this one first. What I change here is one line. I just added this positive part after the first layer, right? So again, this stuff was, we go from n dimensions to d dimensions of the hidden layer. Then I zero out everything that is negative. And then we go from D to capital K, right? So the only difference between these 2 cells is the positive part. Add with ReLU equal. So this is a 3-layer network. I have an input, I have a hidden, and then I have an output value, okay? So there are 2 NN modules here. The first module maps the input, the first layer, to the hidden layer, the D, right? And then they have this other, which is mapping the hidden layer to the output layer. So I have input, hidden, output. I count 3. There are 2 modules, right? 2. I don't know what's that 2. All right, so the only difference was that I added one line. And are you ready to look at the performance? Yes? No? Okay, I'm already late, so I should not waste your time. Yes, okay. There you go. Accuracy 0949, okay? Let's print the model. Ta-da! Okay, you have ta-da too. There you go. Okay. Does PyTorch do the one hot encoding by itself? Yeah, you can check the code, right? So you can change also from SGD to Adam. You can. Oh yes, I think that it changed. So someone can send a pull request, please. Someone fix this stuff. But nevertheless, if you use for both networks, let's use Adam here as well, right? Adam, just to make sure. Adam. Okay, so this one is still 05. Oh, because I think we had to specify. Okay, so now both of them use the same. Okay. I believe that I had to pick a better learning rate, right? I didn't pick I picked the default learning rate here for SGD. Okay. Now both of them use the same optimizer. You still see one works, and the other one does straight lines. Okay. Good point, Randy. Okay. In the last 30 seconds, then I'll let you go. I show you instead this regression, right? So just to be fully, to show everything. PyTorch deep learning. So here I just do exactly the same thing. I apply the 5 steps. Once again, what are the 5 steps? Can you remind me on the chat? Five steps. Forward, loss computation, clear up the gradients, right? Fourth is going to be backprop. Fifth is going to be stepping, okay? Okay. So in this case, I'm going to be trying to do regression, and I try to get to learn this function over here. I start by using just a linear model. And of course, a linear model is going to be just drawing a line through these points. But then let's use like now a few networks. One network with the tanh hyperbolic tangent, and one with the ReLU. So these are my initial networks, right? So these are before training. The networks are giving me basically horizontal results, and they are not green, of course, because they didn't see data, right? Then we fit these curves, right, to our own curve, and let's see how they look, right? So there we go. So in the left-hand side, I use the ReLU, and you can see this is basically a piecewise linear interpolation, basically. Whereas here with the hyperbolic tangent, things are much smoother, okay? Something interesting is going to be trying here a different zooming factor. Let's go four times further away. And so what happens is this following, right? So in this case, the network just goes straight linear because we've been using ReLUs. So the easiest thing to do is just keep going straight ahead. And you can see how the variance here increases, right? Not too much. Instead, in this case, I use hyperbolic tangent. And you can see that as you go away from my training data, you're going to be re-observing this kind of, sigmoid shape, right? And then here, actually, the variance is increases much larger, like in a faster way. So the main point here is that if you train several networks, by observing the standard deviation or the variance between multiple predictions, you can tell how far you are from the training manifold. Okay, so this is actually very a very important part. Okay, so usually whenever you train these regressors, you don't know exactly how well or how bad you're doing. But if you have multiple networks trained on that data, you can always measure the level of agreement or, well, disagreement in order to estimate how far you are from this region, okay? And again, different non-activation, non-linear functions will show different kind of fringe behavior, right? Behavior outside the training region. I took 10 minutes too long. Well, all right. I think that was it, right? If there are more questions, please let us know on CampusWire. We'll take any question there. Thank you for being patient with me. See you next week. Bye. Unless there are email questions. There are no questions, right? It's too late anyway. All right. Thank you again for sticking around. And again, there are recordings for the one that left. Bye-bye.